Hello, my name is Hyegi Min from UNIST, South Korea. I'm going to have a presentation about high-yield analysis of individual ions and molecules through the interior of carbon nanotubes. The carbon nanotube is one of the representative carbon nanomaterials. The dimension of carbon nanotube is nanoscale diameter with micrometer scale length, having extremely high surface area. Because the CNT wall is composed of the highly ordered crystalline structure of carbon atoms with pi electrons, CNTs have high mechanical strength, electric conductivity, thermal conductivity, and chemical stability. Taking advantages of these strengths, CNTs can be applied in various fields such as energy, catalyst, composite, and sensors. However, the interior channel of the CNT has not been explored well. The interior of carbon nanotubes is a nano-confined system. Due to the highly ordered structure of carbon atoms, it has a very large slim length. A high aspect ratio with entire structure uniformity also provide ideal condition for efficient molecular transport. Therefore, carbon nanotubes can be used as nanopore technology for individual molecular analysis. From the 2010s, ions and molecular transport have been reported in various research groups. However, the extremely low detection yield of conventional CNT nanopore platform is a severe problem for further research. To solve this problem, we designed a new CNT nanopore platform. We started from the synthesizing horizontal aligned carbon nanotubes with a centimeter length, and based on the iron catalyst, the small diameter of carbon nanotubes can be synthesized and analyzed in various tools such as the AFM, Raman spectroscopy, SEM, and TEM. Combining with the photolithographic masking process and reactive ion etching, the only desired CNTs are remained and transferred onto the inert polymer matrix through the PMMA mediated transporting layer. These CNTs can be fully encapsulated in the polymer matrix by pouring the low viscous pre-polymer followed by the curing steps. After slicing this block with a thin membrane by using the ultramicrotome, the CNT membranes with the identical number, size, and length of the CNT channels are eventually fabricated. After removing polymeric residues covering the CNT pore by using the reactive ion etching process, the membrane is directly attached onto the glass capillary. After setting the capillary and membrane assembly into the data acquisition system, we can measure the ion conductance by applying transmembrane voltage in the ionic solution. To measure the ion conductance, we repeatedly ramped up the voltage from -1 volt to the 1 volt. Interestingly, the ion conductance increased slowly as we repeat the voltage ramping process. It might be due to the wetting of the CNTs, accumulation of charged species near the pore mouth, and removal of polymeric contaminants. We also observed the current drop events during this measurement. Through this process, around 90% of the CNT membrane showed stable ion current, and 1/3 of them showed current drop events. Then what causes the current drop events? The current drop events can be caused by the channel blockage by a salt cation. When there is a transmembrane voltage across this CNT channel, then proton flux was formed toward the cathode, producing stable baseline ion current. The salt cations dissolved in the solvent are also transported toward the cathode, and they can enter the channel. Since there are differences in the electrophoretic mobilities between salt cation and protons, it causes the disruption of proton flux, occurring the current drop event. When the salt cation escapes from the channel, then the proton flux can be recovered, returning to the baseline ion current. In case of the anion, they cannot enter the channel due to the electrostatic diffusion from negatively charged carboxylic groups. These negatively charged carboxylic groups are formed during the reactive ion etching process. One of the advantages of this platform is the first side exchange of the ionic solution due to the independently movable cis and trans side. So taking advantages of these strengths, we can observe how the blocking event is changed depending on the analyte. For a clear experiment, we rinse the CNT membrane with fresh deionized water before moving into another analyte. Then we prepare the single nanotube membrane that contains a CNT diameter of 1.28 nanometer. We prepared potassium chloride, sodium chloride, and lithium chloride solutions to observe the translocation event of cations of potassium, sodium, and lithium. Based on this current trace data, the values of the conductance change in ion mobilities can be calculated. Interestingly, the electroporating mobilities inside of the CNT channel is different from the bulk mobilities. It might be due to the dehydration of ions and cation pi interaction at the CNT wall. However, theoretical calculation should be proceeded to understand the exact mechanism of ion transport. Then we expand our research to the neutral charged species. Before setting up the experiment, we have to investigate the driving force and direction of the electromigration. The direction of the electromigration is determined by the combination of electrophoretic and electroosmotic flow. Then we have to consider the electroosmotic flow for the neutral charged molecules. In case of the CNT channel, CNT wall is enriched by the pi electrons that contribute to the negative surface charge. The electric double layer is formed at the wall boundary, and the neutral charged molecules can be translocated through the cation enriched diffusive layer toward the cathode. So for the experimental investigation, we use the polyethylene glycol molecules, which is one of the widely used molecule in the polymer physics. Then we dissolve the polyethylene glycol in the trans side, and we apply the negative potential to the cis side to observe the translocation event of PEG from trans to the cis side. And the molecules are randomly diffused near the CNT pore, and they can enter the channel by collision with the proton flux. Through the voltage ramping process, CNT channel is also activated, and we can measure, we can observe the current drop events from the PEG translocation. Interestingly, the IV curve was highly asymmetric like diode devices. The ion current rectification effect can be occurred due to the electroosmotic flow. As described in the previous slide, the electroosmotic flow occurs toward cathode in the CNT channel. And according to the Stokes-Einstein relationship, the ion mobility is inversely proportional to the viscosity of the solvent. When the PEG is dissolved in the solvent, then it increases the viscosity of the solutions and decreases the ion mobility. So here, when the working electrode is cathode, the high viscous PEG is moved toward the cathode, filling the CNT channel by the electroosmotic flow. It causes the low conductance. When working electrode is anode, then the low viscous of hydrogen chloride solution fills the CNT channel, producing high conductance. This phenomena causes the ion current rectification effect resulted in the asymmetric IV curve. Then we recorded the blocking events of polyethylene glycol depending on their molecular weight. We found that the channel blocking behavior, such as conductance change and dwell time, are changed. To clearly understand this phenomena, we conducted statistical analysis. Firstly, we collected the data of the dwell time. The dwell time means the residence time of the molecule in the CNT channel during the channel blockage. So the above graph shows the mass spectra of the PEG used in our experiment. And the below graph shows the statistical histogram of the PEG dwell time in the CNT channel, depending on their molecular weight. After fitting each distribution with a nonlinear curve, we can extract the average and standard deviation. We found that the dwell time is exponentially increased as molecular weight increased. The linear regression was highly matched with our data points. And from the dwell time data, we can easily calculate the electroosmotic velocity of the molecules by using this formula. Then we analyze the conductance change, which is corresponding to change of the ion conductance during the channel blockage. The data are also shown in the histogram and fitted with a Gaussian distribution. We plotted the average and the standard deviation and compared with the theoretical calculation values. According to the Carter counting principles, the conductance change should be increased at the higher molecular weight because the size of the molecule is increased when the number of repeating unit is increased. However, in case of the experimental data, the conductance change is similar regardless of the molecular weight. It means that the size exclusion effect is analogous at every case. To clearly understand this phenomena, we studied the change of the molecular structure in the CNT channel. We organized the corresponding system by using molecular dynamic simulation and observed how the molecule behaves in the CNT channel. As the video shows that the PEG molecule prefer to adhere to the CNT wall, and based on this simulation data, we can calculate the radius of gyration along with the z-axis. The result shows that the gyration radius increases when the molecule is inside of the CNT channel. It means that coiled chain is stretched inside of the CNT channel due to the CNT-PEG interaction, such as van der Waals forces and hydrophobic effect. This data also supports the electroosmotic flow of the PEG molecules in the diffusive layer at the electric double layer. Here is the summary and future perspectives. We reported the development of CNT nanopore platform and showed the activation behavior of CNT nanochannels. We studied about the charged species, especially solvated cations, by calculating the electrophoretic mobilities of each ions. And then we analyzed the neutral species by observing the PEG translocation driven by the electroosmotic flow. Although this research field is a initial stage, the CNT nanopore platform has a variety of applications such as energy harvesting, single cell analysis, water purification, and molecular chromatography. Here is end of my presentation, and if you have any question, please leave any message in my AI poster. Thank you.